It's work that started about last, I would guess, May. They finished their thesis in November last year. And since then, we have been trying to further optimize the system and include everything into LLVM and hopefully also in some distribution of OTP. This is finished work. This is work that fully works, as you will see. Yeah. So without further ado, what is LLVM? It's a project aiming to provide multiple backends for the high performance compiler. It's the native code compiler of Erlang OTP, for those that are not aware of it. Using the low-level virtual machine infrastructure that Frey already talked about, so I will not have to say very much about this. In order to improve the performance of Erlang applications, but most importantly, to ease the maintenance of its native code compiler. We really want to outsource the backends of the native code compiler to other people, if possible. So this talk also has an overview. I will talk briefly about how the HiPE native code compiler looks like, what the LLVM compiler infrastructure is, and then I will talk about the architecture and the implementation of LLVM, what extensions we needed to do to LLVM itself, and the new HiPE component that we have added. And also I will talk about performance, because I think a talk in compilers should actually show some performance, because that's really why you're doing it, besides having fun. And I will show performance, new numbers, compared to Beam, compared to HiPE, and compared to also the Erlang system. So in this sense, this talk is very much different than the one I had in San Francisco. And also I'll talk about the current status and future work of what we have. By the way, feel free to interrupt at any point. So HiPE is a project that started back in 1997 at Uppsala University. I joined Uppsala University in 1999. And since, actually, is Bogomil still here? No, he left. But this was about the time in 1999 that there was a switch from the Jam to the Beam. And the first thing I did, it was actually my first Erlang program, was to write the Beam disassembler. I don't think I needed any documentation, just the zeros and ones were enough. From the bytecode format of the Beam compiler. It's true, it's not a joke. And since 2001, the HiPE compiler has been a component of Erlang OTP. By now, it's a mature compiler in the sense that it's robust and produces reasonably efficient code, given that we are compiling Erlang and we are not compiling C. So there is a limit to how fast you can make it. Because it's a managed language, for example, it requires garbage collection, it requires to manage heaps of possibly different processes and such. It has backends for Spark. This is the first backend. We started with HiPE. And then soon afterwards, we started working on x86 and x86-64 backends. It has a PowerPC and a PowerPC 64 backend, and also an ARM backend. We don't have any other backends because we didn't have any machines to test it on. So what is LLVM? It's a low-level virtual machine, although actually the virtual machine part of it is confusing. It's really a collection of industrial-strength compiler technology. It's very much hyped. It's a language-independent optimizer and code generator. It provides many optimizations. How effective they are, nobody really knows. It supports many targets. It generates reasonably good code. But again, nobody knows how reasonably good is good. It has front ends for Clang, C++, C, Objective-C. Basically, it supports all the things that Apple is interested in for its development. It's designed for speed, reusability, and compatibility with GCC. It has various other tools around it, like debuggers, binutils, standard libraries, various low-level tools with many advantages. It's really a high-level portable assembly. It has a RISC-like instruction set, a static type system. It does everything in so-called static single assignment form. And it comes in 3 different flavors: a humanly readable form, an on-disk form, and an in-memory form. Oops. Now, why did we choose LLVM? Or why would one choose LLVM? It also has a static and a just-in-time compiler, and one can use it also for static analysis of C-like languages. It's a state-of-the-art software with a very active community of developers, especially on the mailing list. I'm not sure that this really reflects the development. Sounds like Erlang, I guess. I guess making a new compiler means making a bit of new glue code, and any components that are not really available, you have to do yourself. And then you can choose some components that exist there, like which register allocator you will use, whether you will use instruction scheduling, order you will use, and so on. Most interesting for this talk and for why we chose LLVM was that it supports many architectures. It supports all the architectures that the HiPE compiler already supports, and many more that we would never think of writing a target for, like Blackfin. I don't even know what Blackfin is, but if we compile to LLVM, we can have a Blackfin backend for Erlang, in case somebody is interested. Or the Emblaze, which sounds more fun, I guess. It's an open source project. It has many contributors from industry, research groups, individuals, people that don't know what to do in their life, and so on. Like us, for example. Now, on a more serious note, this is how the architecture of the HiPE compiler in an Erlang OTP system looks like. I've shown this figure many, many times, but repetition is the mother of all learning. On the one hand, here you have the Erlang runtime system, where you have the Beam emulator, the bytecode that you load in the from file, some other data, the strings. These things are on the one side. Now, if you decide to use the HiPE compiler, what really happens is that you take this Beam bytecode, you pass it through the Beam disassembler, my first Erlang program, and then this creates symbolic Beam, which then gets translated into other forms, lower level forms. It gets translated to something called I-code, which is the intermediate code representation of the HiPE compiler. This further gets translated to a register transfer language, the RTL language. And then it goes into the various backends, the ones that you are selecting to compile for. The generated native code goes back from the loader. Actually, it's the same loader as the Beam these days. It gets loaded to the system, and at the same time, you can have both bytecode and native code happily coexisting in the same runtime system and executing, hopefully, happily together. So that's how it looks like. Just to give you some idea of how I-code looks like, this is the I-code that gets generated for a simple list sum function. This is the actual I-code after it has been translated to SSA form. That's why you see this strange fees there in the top of the code. This is pretty much the code that we generate in label 3, the code that we generate for deconstructing the list and doing the addition. If it is a nil in variable 3, which comes from the first argument, or v6 from the loop, then we go and return exactly what happens to be in v4. So you can just, if you just spend, I think, half a minute on this slide, you will really understand how the I code looks like if you do some pattern matching with what's happening in the on the Erlang level. So I code is actually relatively high level. One can follow it. But then the HiPE compiler goes and translates this to a lower level language. It goes and translates it to RTL. And in RTL, the code looks a bit bigger. It didn't even fit on one slide. It has 42 lines, unsurprisingly. Well, that's how it looks. I will not even try to explain this. What is interesting here is that all the tagging and untagging and all the memory operations are explicit at this level. So at this level, we have a very low-level language. And actually, this is very close to LLVM's intermediate representation. And we can translate from this language to LLVM intermediate representation and then let the LLVM handle the rest, use LLVM as a backend. So what do we have beyond that in HiPE? We have the various backends, and the thing that the component that is very nice in HiPE is the register allocator. Actually, we spend a lot of time in register allocation, and we provide various of them. There are 6 different register allocators. The best one is something called iterated register coalescing, and actually does a very good job. But beyond that, there are not that many things that happen at the backends. There is a bit of frame management, but it's very much standard. We do a bit of special code for tail calls because we have to worry about tail calls in Erlang. And some code linearization paths trying to take advantage of the modern architectures and the way they do caching. But that's it, really. And then the code just gets assembled. There is no instruction scheduling that's happening. There are no other fancy optimizations based on whether you're compiling for a target that has SSE2 or some other fancy thingy. The HiPE compiler is totally unaware of these things. So perhaps by compiling to LLVM, we can outsource some of these things to the LLVM maintainers. So why use LLVM as a backend? I've already said pretty much the main reasons. The main reason that you will not see in this slide is we wanted to have fun. And the students wanted to learn something. And I think they very much succeeded in that. But besides this, we did it basically for curiosity. I wanted to perform a research experiment and see how good is this LLVM after all. Maintenance of the existing backends. If all goes well, we'll replace 6 different HiPE backends with one, just the LLVM backend, and then we'll let the LLVM handle the rest. Also, it will be smaller size and straightforward code. And basically, we're going to outsource everything. Also, we'll get more backends for free. We'll be able to compile to this Emblaze, and so on. And also possibly improve the performance. So let's see what we did. We added just a new component, a new backend to HiPE, which we translate after RTL. We translate to LLVM intermediate representation. We let LLVM generate native code for the target that we are compiling for, and then this native code gets fed into the HiPE loader and gets loaded again as if HiPE has generated this code. That's it. So we actually wanted to use pretty much the same infrastructure, so we used the existing HiPE loader and all the ERT support. And we decided to be ABI compatible so that we don't have to rewrite anything that worked before and existed. Now, the component, what is shown there in the picture as LLVM, is really a bunch of passes. We translate from RTL to LLVM assembly, which is actually humanly readable for those that can read the LLVM, like myself. We can understand what it does. And then this humanly readable assembly, we translate to LLVM bitcode, which then is not humanly readable. Then there are various optimization passes, but these are happening by the LLVM optimizer. And we can choose whether we want a 1 or 2 or 3. Actually, it does not really matter too much in my experience. Them is very small in performance. Then this bit code, after it has been optimized various times with various passes if you want, gets translated into native assembly. And then we impose rules about the memory model, the stack alignment, and all these things. We create an object file by invoking LLVM GCC. And this LLVM GCC then gets translated to ELF64 format that we then gets translated into loadable object and gets loaded into the runtime system while in the normal way that code gets loaded in Erlang. There were some subtle points on using LLVM. We had to write a new calling convention module because LLVM was unaware of our calling convention, what are the special registers of the VM, like the heap pointer and the stack pointer and all these things. We have callee and caller save registers in this calling convention, and the callee is the one that pops the arguments. The same thing had to happen, by the way, for the Haskell guys that were translated to LLVM. They had to also add a new calling convention. We had to write an explicit frame management module, which has inline code for Stack Overflow checks in the assembly prologue. And we also had to do something about stack descriptors to support both exception handling and the precise garbage collector. It turns out that actually LLVM does not have very, very good support for garbage collection, despite all the things that you read on the web. It actually is pretty bad for languages that need precise garbage collection. Perhaps it's good for supporting conservative garbage collection in C-like languages, but if you want precise garbage collection, it's actually not very good. And this is an area that we want to work further. So, we needed to do 3 sets of patches for having this work at LLVM. These were patches to LLVM. They had nothing to do with HiPE. We needed to implement a custom calling convention and a way to ping various registers to and tell the LLVM register allocator that they cannot be used for anything like, for example, the stack pointer cannot be used for something else. And I'm glad to report that this is already part of LLVM's code base. We managed to push this set of changes to the maintenance branch of LLVM, so it will appear in the next release. There are 2 more sets of changes. We need to write a garbage collector plugin and a function pass to emit a custom prologue. These things are not already part of LLVM, but I think they are very uncontroversial, so they will accept them relatively soon. We ran into a problem there because LLVM had this very serious bug that had nothing to do with HiPE or our work. having to do with promoting registers from 32 bits to 64 bits. And we actually have a fix for that. But until they accept it, we cannot proceed anymore. This only affects the 32-bit platforms, not everything. What we've done now and what we have, and you can try it if you want, is a new HiPE component on top of the maintenance branch of R15B, actually of R15B01. It's a full system. It supports x86 and x86-64. It supports accurate garbage collection. And it's in total about 5,000 lines of code. So it's not too big, actually. And this is Erlang code, by the way. So it's medium-sized project, I would say. Of course, they are very specialized lines of code. It's not, hello world type of code. But now, what is very nice is that it's robust. It's very robust, and I think it's ready to use in production. We are testing it against the OTP test suite, and we don't have any issues. We are actually being able to compile itself and bootstrap and everything. So, yeah. So, here's the moment you've been waiting for, the performance. So, before you look into this, let me see what it has. It has, this is on the x86. This is a number of benchmarks. And everything is normalized based on beam being 1. So the gray bar in all these things, I hope you can see the gray, is beam. And this is not the interesting bar. It just appears there so that you don't get confused. So if beam runs in 10 seconds, it means that HiPE, which is the blue bar, runs this in 3.3 times faster. So these are speed-ups. And the green one is the one that you should be looking for, is the performance of ErLLVM. Now, Erlang is also an interesting system to bench against, and we took two different benchmarks. What I write there with Erlang 1, which is the red bar, and what is shown as Erlang 6, which is the yellow bar. Now, what is Erlang 1 and what is Erlang 6? Erlang compiles to Java, to the JVM, and then uses its just-in-time compiler. So what we've done in these benchmarks, we are measuring the first time it takes to execute these benchmarks. These benchmarks actually have a number of, they run for a number of iterations, so it's not you run it only once. But in any case, we are measuring the time it takes to run the benchmark once, which is Erlang 1, and the time it takes to run. So we stop after the first run for some seconds, I think 1.5, 2 seconds or something like that, to allow the just-in-time compiler to kick in and compile whatever it feels like. So we run then the second benchmark. We stop again for 1.5 seconds. The compiler just kicks in and might compile something more. We do that, and we measure the sixth time. By the sixth time, pretty much everything should be able to be compiled, or everything that it feels like should be compiled to just-in-time compiled to native code. And actually, you can see what the numbers are. There is not that much difference, really, between the first time the code gets run with Erlang and the sixth time the code runs. The only difference is this lists test, where there is a significant difference. In the other ones, the difference is relatively small, so don't expect really too much from even a very mature just-in-time compiler. That's, yeah. Yes?
What about the recursive?
Yes? What about the recursive?
I mean, Erlang is significantly faster.
Yes.
Do you have any comments on that? What's the test for that?
I can show it to you. So there is also this one that says average, and you can see sort of pretty much what you can expect on average. You can expect something like 2.5 times faster execution with native code on the average, and you can expect something less than 2 times with Erlang. What's even more interesting is, well, this is the same thing, but on different type of benchmarks. I think these ones actually were from the first ones. These binary trees, Kameneos, Fankuch, are from the shootout, the computer language shootout benchmark game. You probably, some of you may have seen this. Yeah. So these are smaller benchmarks that have been used at one time or another to benchmark different things. I have to note that Erlang is not a very robust system, at least not yet. There are like pseudonode and the eStone that you get crashes with Erlang currently. I don't know why this happens. And Orbit, actually the Orbit is an interesting one, and it's a big benchmark. It's like, it has multiple files, and you know, it's not a toy one like the other ones, like many of the other ones at least. Again, pretty much a similar picture you can see here. Now, this was also on the x86-64. On the x86, you get these. For technical reasons, we didn't manage to get Erlang to work on our 32-bit machine yet, at least. We are trying on it, but perhaps there is something in our part that is wrong. So I will only present numbers for Beam, HiPE, and LLVM. Again, here, you see that HiPE in some cases, or actually in many cases, is a bit faster still than LLVM. In some other cases, LLVM is a bit faster, especially in old matrix and body and Mandelbrot, and this nested loop also have floating point numbers. And LLVM is able to actually take advantage of modern architectures better than what HiPE does on the x86. The same, well, benchmarks like the previous ones also on the x86. Again, you can see that on average you can expect something like 2.5 times faster with native code execution, both when using HiPE and when using LLVM. That's pretty much it. Let me do you a non-impressive demo, just to show you that this thing works. So I have here which ErL, and you can see that my ErL is pointing to my LLVM system and not the one that you get from Ericsson, which I guess is the one that you get from Ericsson plus more. So if I do ErL, you get the latest version, but it's just patched with the LLVM additions. I have some Mandelbrot thingy that is actually let me, how? I can, for example, run on a 500 by 500 two-dimensional array to do Mandelbrot in 100 processes. And you will see my HTOP that does this sort of thing in parallel. It's a very nice parallel benchmark. It's all green. It means that there are no locks and such. And this goes on for a while. And this will, when it finishes, it will print out the number of seconds that it took to finish. And you can see that it goes on very, very green. It's a very nice parallel benchmark. It's really a joy to see that Erlang OTP, when you write careful parallel code, it's really very nice with the schedulers. This is besides this talk. But it finishes in something like 44 seconds. So let me now compile this to LLVM, invoking the HiPE compiler. And you can see that it has finished. And let me just run this again. And you will see that it will take less time, hopefully. Otherwise, it's not a very nice demo. It's not very impressive anyway. I just put the other one so that you can see something colorful. But it finished in 18 seconds as opposed to 44, so it's about 3 times faster. Yeah, okay. That's all for demo. The performance as you get is much better than Beam. It's almost as good as HiPE. Sometimes it's actually better than HiPE. It's a smaller code base. It's a simpler code base for the backends. It opens up the possibility to target more architectures, like the Emblaze. And also, as LLVM matures, all the improvements of the LLVM backend will also improve the performance of Erlang applications. On the other hand, if LLVM tomorrow might have something, performance degradation, we'll also have the performance degradation. That's what you get when you rely to other people to do your job. Currently, there is a downside. You need to download and install the custom LLVM. As I said, not all are patches. We have 3 sets of patches, and only one of them is in the main LLVM branch. Hopefully, we'll push the other 2 sets of patches to them, and then you will not need to download and install the custom LLVM anymore. It has slightly longer compilation times, but it's actually not a problem at all in practice. As you saw, the compilation is pretty fast. We are still communicating through files, which means that we cannot do everything really in parallel. But as you saw, compilation times are not really a problem right now. For future work, we are trying to finish pushing the LLVM patches upstream. We are working on an ARM port. And more importantly than everything, we want to improve the GC support, because actually that's the thing that causes occasionally the LLVM to be slower than HiPE. I can get into very technical details, but you probably don't want to hear right now that. It's not a trivial job. It will take a while, because we need to actually give proper support to LLVM for garbage collection. And this is a general issue. It's not related to Erlang. All this thing exists in a site that has this fancy logo here. It's llvm.softlab.ntua.gr, where you can get the system and play with it. You can download it. It has Erlang OTP R1501 plus more. So you will not really miss anything if you're already working with Erlang OTP R1501. That's it. The site again in a bigger font so that you can read it. The code is all on GitHub. You can test it yourself and measure. You can, if you find something that is interesting, please report your experiences to us. There is even a mailing alias that reaches all developers, and you can find it on the site. And you can contribute to the project in any way you see fit. We are looking for guinea pigs. That's it.